Hey, let's begin with the sequences and series. In this lecture, we're going to introduce to you new term known as series. In the previous lecture, we have discussed about the term sequences in details. We discussed about convergent sequences, divergent sequences, and oscillatory sequences. We also discussed about boundness of sequences. We discussed about bounded and unbounded sequences both. And now let's look at between analogy of both these terms, sequences and series. So sequence is just given us the terms noted in any order or sequences. But series is the sum of the nth term of the sequences. So series is denoted by sum up to nth term. It can be sum up to one term, it can be sum up to second term and third term up to so on and up to infinite terms. So in this lecture, we're going to discuss about specifically the term known as infinite series.
Infinite series. If un sequence is a sequence of real numbers, then the expression u1 plus u2 up to u infinite is known as infinite series. It is denoted by sigma, where n will go from n equals to 1 up to infinite of un. And let's look at the one more term known as partial sums of the series. So if sigma of un, n belongs to 1 to n, and it is known as of an infinite series where the terms may be positive or negative, then Sn is known as the nth partial sum of the sigma n, sigma un, which is known as infinite series. So S1, S2, S3 are the first, second, and third partial sums of the series, and hence Sn sequence is a sequence of a partial sum of the series. Now let's look at some behavior of infinite series. So as we look at the partial sums, uh, it behaves similar. Infinite series will behave like its some partial sums up to nth partial sum, or up to one partial sum, up to second partial sum. So it behaves similar like every series, every sum of series, any partial sums, which is either nth or anything else, any term up to one term, up to second term, up to nth term. It may be any of the following. So it will behave similar like it. So if it diverges or oscillates respectively, either converges or diverges, if the sequence of the partial sum converges, diverges, or oscillatory, and in the similar manner infinite series behaves similar like partial sums of a series respectively. Now if sigma un is convergent, if limit n approaches to infinity, Sn is a finite quantity, and is also it is divergent if only Sn is a partial sum, we know that is an infinite quantity. So if it is infinite quantity, we know that it must be divergent, partial sum must be divergent. So similar way, our sigma of un, which is infinite series, is also divergent. And the third point is, if sigma un oscillates finitely, if sequence Sn is bounded and neither converges or diverges, which means partial sum oscillates finitely because it is a bounded sequences. And in the similar way, if it is oscillates finitely, infinite series can only be oscillates infinitely if and only if sequence Sn is unbounded and it neither converges nor diverges, that is partial sums oscillates infinitely. So in the similar way, the infinite series will also oscillates infinitely. Now let's look at some examples. Now we have to discuss the convergence of the series. of the given series. Here, un is 1 upon n, n into n plus 1, and we can use our partial fraction method equals to 1 by n minus 1 upon n plus n. Putting n equals to 1, 2, 3, and up to n, we get u1 is 1 minus 1 upon 1 minus 1 by 2, u2 is 1 by 2 minus 1 by 3, using this particular formula. So this is the formula we have used, and we just get our following answers. Un is 1 upon n minus 1 upon n plus 1. When we add of these or all the sequence of the all these terms together, we will get our sum of the given series. So Sn is 1 minus, so as we see that this will cancel this and this will cancel this, and up to we will see that this will left left the uh, of this un will be cancelled out with the un minus 1 right term. So we will left with only after it 1 upon 1 minus this last term, which cannot be cancelled with any of the term. So we will left with 1 minus 1 upon n plus 1. So limit n approaches to infinity Sn, which is by putting n approaches to infinite, we will get 1 minus 1 upon infinity, which is 0, which is 1 minus 0 equals to 1. So as Sn implies that Sn sequence converges to 1. Sn and therefore we get infinite series which we have given, which given to us, should also be converges to 1. Now let's look at the another example of divergence of the series. So if Sn is 1 square plus n square up to so on, which is also denoted as sum of the squares of the numbers, which is n into n plus 1 into 2n plus 1 upon 6 whole upon 6, we will get, as n approaches to infinity, we will obviously get plus infinite. So because this term is infinite, infinite in infinite will become obviously plus infinite. So therefore, this sequence diverges to plus infinite. The given series diverges. This implies that the given series diverges to plus infinite. By looking at the relationship between the any particular nth series and up to infinite series, we can deduce that the fact that if it is converges up to nth term infinite to plus infinite, and if it is infinite series, if it is n Sn series, it means partial sums. If it is diverges to in plus infinity, then whole infinite series should also diverges to plus infinite. And now let's look at the third
It's
example.
21 hours.
Show that the series n equals to 1 uh, goes to infinite, and it is n into minus 1 whole raised to power n oscillates infinitely. So Sn is minus 1 plus 2 minus 3 plus 4 minus 5 plus up to n terms. We will get minus of n plus 1 upon 2 if n is odd, and n by 2 if n is even. The subsequence Sn as 2n minus 1 diverges to minus infinite, because this is odd sequences, because here it is, if we put infinite and as n approaches infinite, it will definitely whole thing will become minus infinite. So in this case, if n is even, so it should be n by 2 will also goes to plus infinite as n approaches to infinite. So this subsequence, once we know that it is oscillative sequence, so we can just simply say that, so it is one time it approaches to minus infinite and another time it approaches to plus infinite up of any partial sums of the subsequences, and then we will it implies therefore Sn oscillates infinitely, which implies that our sequences of a series of infinite series should also oscillates infinitely. So that's the whole idea about today's lecture.
I hope you enjoy my content and please don't forget to like, subscribe to my channel. Till then, keep learning and keep exploring. And as always, free to email me at dsvfx6789 at gmail.com.